Hello everyone and welcome. Today I would like to talk about binary tree paths. So given a root node of a binary tree, return all the root to leaf paths in any order. For example, 1, 2, 5. So this is joined by this dash and larger sign like an arrow. This is another example, 15, 7, 11, 13, and 12. And you also notice that the number of nodes in the tree is within the range of 1 and 100, which means the root node cannot be none. So how can we return all the root to leaf paths? In general, there are two solutions to this question, known as recursion and iteration. They are considered to be equivalent to each other. So now let's know the code implementation in more details. On the left-hand side, we have the code using recursion. It has the DFS depth first search function called itself recursively by visiting the left subtree first, followed by visiting the right subtree until the terminal leaf node. So if you follow the mouse cursor, the traverse path is like this from the root node all the way to the left subtree, backtrack down to the right subtree, backtrack down to the left subtree, backtrack down to the right subtree, backtrack down to the left subtree, right subtree, right subtree, and then left subtree, right subtree, and all the way through all the possible nodes, terminal leaf nodes. So that's the recursion code implementation. On the right-hand side, we have the code using iteration. And it's easier to understand this code by turning the tree upside down. This is because we always pop the last item at the top of the stack to process. And so the node that's closer to the root node is being pushed down at the bottom of the stack for processing, and near the top, always closer to the leaf nodes. And you also notice that if node.right and if node.left is in the opposite order, as opposed to this recursion implementation, this is because we want to process the node left first using the pop. Okay, so this is the implementation using both, and they are considered equivalent. In either implementation, we visit the left subtree first and then the right subtree until we reach the terminal leaf nodes. This approach allows us to find all the possible paths in this binary tree. For this question, we're going to leverage this general approach while adding a string variable to keep track of the unique path, and then aggregate them together to return an array of all the possible paths. With the background introduced, now let's write the code. First of all, we're going to implement the solution using recursion. I'm going to remind ourselves the general recursion solution from our background introduction. So we define a DFS function and with the node as an argument. And if the left subtree exists, we call itself again to visit the left subtree. If the right subtree exists, call itself recursively to visit the right subtree. Finally, if neither of them exists, we know we have reached the end. And then we're going to have we're going to call DFS within this binary tree path function here. using the loot. Okay, and in this question, we're going to return a resource array for all the possible paths. So we declare a result as an empty array first, and we're going to add just one more argument for the particular path, and then it will begin with the loop value as a string variable here, and it passed to this DFS. And if the left subtree exists, we know we will add an error and the string variable of the left node's value. And the same thing, we can do it for the right channel. This way we can recursively add this arrow and the child node's value. And if we are reaching the end of this particular path, then we simply append this path to the results array. And finally, we'll return result. And that's our code. Okay, so let's submit and to see how it works. We submit and done. So it's passed all the requirement here. It's good. Now we will analyze the code for complexity. First, for time complexity, since we need to traverse all the nodes in this binary tree, so it will be ON. And then for space complexity, let's focus on the recursion stack here. So this recursion stack will be OH for a balanced binary tree, and H is the height of the tree. Okay, and in case the tree is very unbalanced, H equals to N. So generally, it will be between the N and N for balance to balanced tree. Okay, and then for space complexity, we can also look at this results array. This results array typically would have O log n. So the space complexity is definitely driven by the recursion stack here. Okay. Now we can also try to convert this code based on recursion to iteration as well. So we know in the iteration implementation, we have this while stack loop, and the stack initially should have the loot value, and since we have two variables here, let's use a tuple. So the loot node and the string variable of the loot value, and then before that we have a resource empty array, and then so while stack is not empty, we know we will pop the very top item, so it will be loop node path from stack pop. Okay, and then let's follow through. So if loop left exists, then we know we will push. Okay, so stack append a tuple node left and this part. Okay. Okay. So, okay, and we also know in stack we swap the order of this left and right, so the left gets to be executed first, when it pops. Okay. Although for this question, it doesn't really matter the order. And so we will have the same here for if no right exists. Okay, we modify this to be no right and no right here. And finally, if neither of them exists, we know we can append the path to result, and that will be our code using iteration. And let's test how to see how it works. We submit, and it's done. It's pretty good. It again passed the testing for this question. So finally, let's also analyze the iteration code for complexity. Again, it has this time complexity or n, since we need to traverse all the nodes in this binary tree. For space complexity, so instead of the recursion stack, we have this iteration stack. And also the same, it will be OH for balanced binary tree, and H is the height of the tree. Typically it will be O log n through ON for balanced to unbalanced tree. Okay, all right. So that's all for this question. Hope you find this video to be useful. Please subscribe and stay tuned for more videos. Hope to see you next time soon, and goodbye.